Hello, I'm Joe McEntee, Group Editor at IOP Publishing, and I'm here at Stanford University to talk to Tom Baer, Executive Director of Stanford Photonics Research Center, about the first 50 years of the laser and the next 50. Thanks for joining us, Tom.
Welcome, Joe. It's a pleasure.
The laser is really one of the great inventions of the 20th century. Can you try to sum up the technology's revolutionary impact over the last 50 years?
Well, the laser has had a remarkable impact on a number of different areas of modern society. It is one of the major technologies behind encoding just about all the real-time information we receive. Certainly all the information over the internet, almost all of our voice and data transmission is done by encoding it on a laser. When you think of DVDs and CDs or videos and audio information, that's all both using a laser to print the DVD and CD as well as to read it and to be able to listen to it and enjoy it. So essentially all of the information we receive is in some way involved with, has been encoded on a laser beam. Lasers are used in our manufacturing, our airplanes and automobiles. They cut the sheet metal, they weld it, they make the parts that are parts of jet engines, the components in jet engines and our automobiles. They heat treat the metals, they cut our clothes, they process our food. And when you think of it, almost all of our commerce these days is barcoded. That's all read by lasers. And even when you order something over the internet, that particular information is transferred to you by a laser. So almost all of our commerce today is in some way enabled by laser technology.
Tom, you're one of the main movers behind LaserFest, a year-long outreach event to mark the 50th anniversary since the first demonstration of the laser. Can you tell me more about the goals of this initiative?
Well, there are several goals, Joe. One of the primary ones is to recognize and celebrate some of the early pioneers, many of whom are still with us today, even though the laser was developed 50 years ago. So part of the motivation for LaserFest is to take advantage of this opportunity to recognize and celebrate this major innovation. We're also quite interested in illustrating the story behind how the laser developed, how basic investments in research, in basic science, really resulted in an innovation which has had a major impact on our economy. And then to show to the general public how the laser is kind of an invisible wheel. It is an integral part of our daily lives in many ways that people don't recognize and they just take for granted today.
So, as the head of Stanford Photonics Research Center, Tom, you're known as a big advocate of multidisciplinary science. Why are multidisciplinarians the future of laser science and technology?
Well, laser physics by itself, it requires many disciplines, and for example, there is quite an important aspect of material science, of optics certainly, electronics, of atomic physics. All of these elements are part of designing and developing new lasers. And in fact, now the newest lasers use accelerators, so even accelerator physics is a part of the newest generation of lasers. But beyond that, lasers are used in almost all the areas of the physical and life sciences, in environmental monitoring, in geology, biology, chemistry, and physics. Lasers are a part of these, integral part of these disciplines. And to use lasers in spectroscopy in these disciplines often requires a multidisciplinary team.
So what can physicists in particular contribute to this multidisciplinary endeavor?
Well, I think physicists play a key role. Physics is really a quantitative science, and physicists are trained to do experimental science in a particular way. The physicists are trained to look at systems and extract the important variables, figure out ways to measure those variables, and then develop mathematical models to predict what those variables would be according to a particular theory, and then to develop the technology to compare theory and experiment. These are techniques and approaches towards doing science that can be applied across a wide range of the life sciences and physical sciences. So what I tell the students that I interact with at Stanford that are in the physics or applied physics area is really think of yourself as being trained in quantitative science. And this training can be applied across the whole range of science as well as in other areas of sociology and economics and psychology. It's really a method of approaching problem solving. And physicists play a key role in this multidisciplinary activity because they bring this expertise in quantitative science to the team.
So just one final question. Looking into your crystal ball, where do you think laser technology might be 50 years from now?
Well, lasers has some very unique features, and what's really exciting about the field now is we continue to see almost a Moore's law improvement in these key features of temporal coherence and spatial coherence and brightness. So, for example, we have lasers that are now many orders of magnitude brighter than sources than we've ever had before. A good example of that is the National Ignition Facility, which can it has a laser the size of 3 football fields that can generate 2 megajoule pulses. To give you an idea of how much energy is in a 2 megajoule pulse, this is the amount of energy that's contained in a stick of dynamite when it explodes. That energy can be focused down to the diffraction limit to a volume much, much smaller than the diameter of a human hair. And when you have that much energy being delivered to that small a volume, you can compress substances down to many times their natural density. So, for example, you can take hydrogen or deuterium and compress it down to a density 100 times that of lead. And when you make that type of a new state of matter, it actually undergoes a fusion reaction which turns the hydrogen into helium. And this allows a tremendous release of energy, which could be an energy source of the future. There's enough deuterium and energy stored in our oceans to power the Earth at its current energy needs for the age of the universe. And so it is a tremendous resource for non-carbon-based energy, which we would have access to. Lasers are also known because you can focus them very tightly, and you can utilize this property of a laser, for example, to encode information on a magnetic disk to a much greater density than you can today. So rather than terabytes on a magnetic disk, we'll be able to put petabytes on a disk. To give you an idea, if you have a petabyte in your PC, you could store all of the movies that have ever been produced on your PC at high definition on the hard disk in your PC. Another property of lasers is their temporal coherence. They are very precise clocks. They are so precise that we should be able to detect the drift of fundamental constants like the fine structure constant that determine the properties of the electromagnetic field, or the gravitational constant that determine the properties of gravity. As the universe expands, we expect these constants may slowly change as the space-time environment around the Earth changes. We should be able to measure the slow drift in these constants using these very precise clocks. So there is a tremendous capability that is inherent in the laser technology that keeps growing and growing, and we expect this evolution of the technology to continue over this next several decades.
So plenty more advances to come.
Absolutely.
Thanks very much for joining us.